want to find out about application I/O, there's a few places in the stack that we talked about that you could be looking for information. But what we're going to focus on is the top part of the stack, which is what your application itself is doing and what the libraries that are linked into it are doing. And I'm not going to talk a whole lot about the file system and storage devices except for the implications of what your application is doing, how they might be affecting them. And our favorite tool for this kind of thing is Darshan. This is something that we developed at Argonne, but it's available on a lot of the machines out there now. So what is Darshan? You don't have to modify your code. You just compile your application, and Darshan gets linked in to intercept your I/O functions. At the ALCF machines and also at the NERSC machines, if you just log in and don't do anything, it'll be turned on for you. It's an automatic thing. Other systems have it on optionally. You can load a package to get it. And the reason we're bold enough to just turn it on is because it doesn't really impact your performance any. For most applications, it will add a few seconds to your MPI finalize call, and that's about it. And what you get from using Darshan is that once your job completes, you get a little log file. I'll tell you where to find it. That has a summary of what the I/O looked like for your application. So what's in that log? You get counters, how many I/O function calls were made. There's a tiny bit of information about high-level libraries. It tells you what your alignment was like, when the opens and closes happened, how much cumulative time was spent. And so just sort of summarizes sort of what are the key things, or the things that we have kind of by trial and error decided are important for understanding I/O. As I mentioned on the last slide, it's just intercepting function calls transparently. The MPI compiler script does this for you. You don't have to take any particular steps other than making sure the package is loaded if it's not already. And it works with C, C++, and Fortran, and I should have put Python on there too. With some work, you can make it work with Python. It doesn't work out of the box with Python, but if you're big on Python, I can give you some tips on how to do that. There is a big caveat though. I've got this on a later slide, but I should go ahead and get it out of the way. On Mira, right now, Fortran 90 does not work with Darshan. So I apologize if you have a Fortran application and you want to look at Darshan, you're not going to be able to do that on Mira today. It's not a fundamental Darshan problem. It's just we have an incompatibility right now to work through. So we'll try to get that sorted out, but it won't happen today. And what Darshan does as your application is running, it takes a tiny bit of memory off of each process and uses it to store its counters. When your application completes, it aggregates all this information together, it compresses it a little bit, and writes it out as efficiently as we know how. And this is a platform independent. It works on Linux and BlueGene and Cray systems. So in practice, if you want to use this on Mira and you're not using Fortran, then what you're going to do is just run your application. You don't have to do anything. And then once your application is done, you look in a directory. On Mira, it's going to be this directory right here, /projects logs Darshan. There's a similar directory elsewhere on the NERSC machines on Edison. And I don't know what the directories are on some of the other systems, but it's turned on by default at NCSA systems, and if you're using Oak Ridge or Los Alamos systems, you can optionally turn it on, and they probably have documentation there about where to look for the log. But if you go in that directory, there's going to be a breakdown of year, month, day, and then your username and app name with some identifying information there. So you can go find your log and copy it out. For it to produce this log, your application must run to MPI finalize time. So if you hit a wall clock limit, either inadvertently or on purpose, just because that's your usage model, you're not going to have a Darshan log. So that's another drawback. If you're in that mode where you routinely hit wall time to kill your application, then you might need to do a special run that actually does stop gracefully at the end so that you can get a log to look at. Anyway, once you have the log file, you've run your job, we've got a collection of tools that you can use to look at it. There's a lot of information in there, and some of it's a little hard to wrap your head around. We try to help with that a little bit, and I'll tell you more about those tools. So the main one that people almost always go to first is called Darshan Job Summary. Apologize that the graphics didn't come out here, but you run Darshan Job Summary on one of your log files, and it gives you a PDF. It's 3 pages full of graphs about what your I/O look like, and I'll highlight what a couple of them are here. The first things you want to look at. These 2 bar graphs tell you what percentage of time was spent doing I/O in different categories. The one on the right there is showing how much time was spent doing MPI/IO. So this application spent, you can eyeball it, maybe 1/5 of its time doing MPI/IO calls. So you want to look at that first, because whether your I/O is good or bad, if it's not making up much of your runtime, I can't honestly tell you should spend time looking at it. But if you look at that and you really think you could get more science done, if you squish that part of the bar graph down, then you should be looking at this stuff if you can. There's some histograms here. This one's pretty important. It tells you, once you get to the file system level, how big were the I/O accesses. We were saying earlier, bigger is better, so you want this one's very good. All the I/O is in a multi-megabyte histogram bin here. If you look at this and you've got a big bar over here, you're probably in trouble. You need to do something or turn on an optimization that'll clump those together for you. And there's some summaries about your file usage, how many files you opened, how big they were on average, that sort of thing. And on the next page, you'll see some timelines that show the range of times over which your application was doing I/O. There's a few categories there that it's broken down into. This particular timeline is showing write access, and it's not super precise. Darshan can record when you started doing I/O on a file and when you stopped doing I/O on a file, and it draws a line between those 2 points. So it doesn't really know how I/O is scattered during those times, but at least this can give you an idea of when during the runtime you were doing I/O and how long that time span stretched. This is a pretty interesting example because there were different subsets of this application that were doing I/O at different times. So you kind of see these chunks. This is time moving from right to left on the chart, and that's MPI ranks on the y-axis. So a little group, well, relatively little, this is a huge application, was doing I/O early. Then another subset was doing I/O for a little while, and then most of the I/O was happening from the rest of the processes a little bit later in the run. So there's kind of 3 tools that you are most likely to use if you're digging into a problem. The first one in this list, Darshan Job Summary, that makes the graphs that I just showed you. It gives you a nice PDF file that you can just kind of flip through. And of course, ask us or email us if you have questions about what it means. The second one is just a variant of the same tool, and it makes the same PDFs, same graphs as the other one, but it splits the data so that you get a separate summary for each file that your application opened. So maybe you're opening a config file, maybe you're doing multiple checkpoint files, whatever. You'll get a separate PDF file that tells you just what happened on that file. So that's a helpful debugging tool if you're doing multiple styles of I/O as your application is running. Maybe you can see something different about, this one's doing something really good, this file, something bad's happening. So some people find that helpful. And then the last one on the list is Darshan Parser. That's just the raw, it gives you all the raw data out of the log file, just spits it out in text format. So that's not something you really want to be staring at. It's kind of like looking at the matrix, but if you know what you're looking for, you can just kind of grep through it for, for example, an easy one is just to grep for the word write in the output, and it'll show you all the counters that are particular to write operations. And there's a lot more detail there than what you see in the graphs. The graphs are just kind of summarizing a few things that we think were helpful, but there's more in there if you dig around. So, if you look at one of these logs, there's a lot of different things you might see. Sometimes it's not always obvious what's going on. So what I'm going to do is spend some time going through some examples. Not picking on applications here, but I just want to show what you might see in a graph and what that means could be happening in your application. And this might give you some clues if you see similar things in your application, what you might want to do about it, or what it might mean at least. Sometimes you can't do anything about it. So The absolute simplest thing you can do with Darshan is just, you know, write down what you think your I/O is like, you know, how many files you're opening, how big the accesses are. Look at Darshan and see if it agrees, because you might simply find some bugs, or, you know, maybe someone did some code modifications, you weren't looking real closely, and it's doing something a lot different than you expected. This is a pretty harmless example, but just to show you. This application is actually a library, a domain-specific library that intended to open and write 128 data files and a little metadata file. For each of those data files, 128 of them, there should have been a header, so a 40 kilobyte write for each file. So, you know, we knew that. Code had just been written. This was fairly early in its development, and so we ran the Darshan summary. And there's a table here that shows the most common access sizes, which actual I/O sizes occurred most frequently. And there's some huge ones, 64 megabyte writes that were the big data writes that we expected. There's the 40 kilobyte headers that were being written by the application. And we looked at how many there were, and instead of 128 of them, there were 512 of them. So as it turns out, this was just a simple kind of coding typo in the code. So what was happening is that every time a data file was opening, 4 processes were writing the same header. Probably this wasn't a huge performance problem, especially at the scale that this example was showing, but you're making the file system work harder by having conflicting writes go to the same point when you didn't, and there wasn't any reason for it. It was just a typo. This is a little bit more involved example. This was one where you know, this is kind of the classical have an application is doing everything it's supposed to be doing. Things are fine, except I'm not getting as much productivity out of my hours as I thought, and seems like it's spending a lot of time writing data. So this is a HSCD application example, and the important thing here is you look first at that graph that I showed. That'll be the first graph in the summary, and it's spending 40% of its time doing I/O. That wasn't the intention. It's just dumping some data, and we couldn't reduce the data. I mean, it was writing data that needed to be written, but when we looked at the file count summary, we saw something interesting. There's 8,000 processes in this example, and this bar graph gets worse as we scale up. But there were 16,000 files, so there's 2 files per process, which is a lot for the system this was running on. And so, you know, is that a problem or not? What we found, and this isn't something that you can get directly from, well, maybe there is now actually, but the problem is that almost all of the time that was spent doing I/O was spent doing metadata, which means the time was consumed by open, by close, by stack, calls like that, rather than actually the time spent doing reads or writes. So they were burning their time managing this number of files as opposed to doing productive you know, I/O operations. So we worked with the scientists in this case and made some code modifications, and we tried a couple of things. One easy one was just to, if they're going to open, you know, many thousands of files, or even more as they scale up, why don't we just create them all ahead of time? So a script runs on the login node, creates a bunch of files, then you run your job. And so at least the application doesn't have to bear the cost of creating all those files and coordinating the updates. And that made a huge jump from 56 megabytes per second to over a gigabyte per second. So that was great. They still weren't happy about having this many files. We weren't getting that much out of it. So the next change, which was actually a code change to the application, was to move to one big shared file and use collective MPIO operations to write it. So once they did that, their number of files went from 16,000 down to 8. The file's a lot bigger, and they're, you know, somewhere around 15% of their time is spent doing I/O instead of 40%. So that won them back a lot of computation time in their allocation in this case. Another one that's a little bit more involved. This is an analysis library, and it writes some big chunks of data in sort of a format of its own devising, and is fairly straightforward. There's some headers mixed in there that describe the data and some bigger chunks of analysis data that are being written. It was written by people that know a lot about this stuff, and they did all the right things. They're using collectives, using MPIO. There's not that much data, and they're doing it the right way. But when they went to scale up this code, what they found was that as they went from 8,000 to 32,000 processes, they expected the total execution time to go down, and it did a little bit, but then it came back up. And the reason is because the I/O time kept getting worse and worse as they used more processes. And so it wasn't obvious from looking at the code why there was a problem here. So we looked at the Darshan output, and I'll actually start with this bottom slide. This is the view of over time how the shared file I/O happened. And there's some reads and there's some writes, and we knew there would be reads and writes. But the thing that was surprising is that there was a time period for the application where it was both reading and writing. And if you looked at the code, there was nothing that indicated that should be happening. And the reason for this was actually, one of the optimizations that I talked about earlier, data sieving, was happening, but it was backfiring. Data sieving was happening here in a case where there wasn't really any reason for it to happen. So what was going on, if you look back at this layout, all the headers were being written first. Header here, header here, header here, header here, leaving gaps in the file, and then they were coming back and putting the data in place. And that made sense from a coding point of view, but what it meant is that when you actually went to do the I/O, you were filling in all these little holes that were scattered through the file. And of course, MPIO saw this and did the best it could, which was data sieving. But really, with a little bit of work, we could just reorganize the code so that the headers were written at the same time as the data, or just before it, so that instead of leaving big gaps and then coming back and filling them in, you wrote a chunk through the file. And the result is that it split up the reads that we knew were going to be happening and then the writes that we knew were going to be happening. And it just made a huge difference in performance for this tool. Well, I guess I spoke a little ahead of the slides here, but the net result was that now it scales like it's supposed to. The I/O time is constant. It's writing the same amount of data. It's a strong scaling example, and the execution time is getting better as we go up. So this was a big win. Another one, this is the one that we didn't expect to see. This is one that we just found kind of mining through logs to see what people were doing. One thing that can happen is you have a certain data set. It's a certain size. Your application is going to read the whole thing in. So this is sort of a checking your conditions kind of thing. In this case, we knew that based on the number of files this application was using, it's 1,000-something files. They're a gigabyte each on average. So there's a little over a terabyte of data that the application can read in. That's all there is. But when we look at the amount of data that was actually transferred in another table on that job summary screen, we saw that it read 500 terabytes from the file system. There's only 1 terabyte there, but it's moving a lot more than that. And the reason for this is that many of the application processes were reading the same data. Now, this isn't a deal breaker for application performance, but it's sort of an unfriendly thing to do to the system. You're multiplying the amount of traffic on the network and passing through the forwarding nodes by a factor of 500. The more efficient thing to do, if you can organize your code that way, is to either use collective I/O, so you read the data all at once and get it where it needs to be, or if you can't do that for some reason, have someone read the data and broadcast the data to the other processes. You don't want everyone on their own reading the same files over and over, at least if they're big. In this example, this is one that's pretty easy to spot if you look at the graphs that you get in the job summary. This is the access size histogram, and the greens are writes. This wasn't that big of a job. I don't know if it says how large it was. I want to say it was just a few thousand processes, but if you look at how many writes they're doing, there's nearly 6 billion write operations, and they're all less than 100 bytes. And if we go break it down further with the table that shows the most common exact access sizes that were used, the majority of them were single byte. There were some 15 bytes and 24 byte. And this was going to a shared file, so the file system was seeing several billion one little byte writes to a file that had locking and everything else going on, and it didn't get much better from there. So as a result, this was a pretty big application, and each process was getting about a megabyte per second of I/O, just because the storage system was being forced to kind of untangle so many billions of write operations to move that data. And then this is one, I mentioned earlier that metadata overhead can be a problem in the HSCD example. So how do you figure that out? We don't have I don't think we have a table in there that shows the percentage of metadata overhead. Maybe we should add that. But this is another example where we looked and it was spending 20% of its time doing I/O. Whether that's good or bad depends on your application. But when we looked at the operations that were happening, this is a histogram that shows a count of how many different types of I/O operations were used. There's a number of writes, 600,000 writes, so maybe that's what they needed to do. There's 200,000 opens though, and another 600,000 stat calls. And this was with 40,000 processes, so a pretty big job, and it spent half of its time doing I/O. So the problem is these 200,000 opens and 600,000 stats were consuming time, even though they weren't really productively moving data. So this is a candidate for, frankly, there's not really any reason for a single application to call stat 600,000 times. That probably worked fine on some system, and it became a problem on this system, and I'll go on a tangent a little bit to tell you why. This kind of feeds back into the you have a lot of bandwidth at your disposal, but latency can be pretty bad. Stat is a good one to pick on because stat can be used for kind of sanity checking. Maybe you run it once at the end to make sure the file's the size you wanted, or maybe one process checks to see if a file has the right permissions on it or something. But it's not something you want all your processes to do simultaneously because it's a hard thing for the file system to do. And the whole reason that stat is difficult for the file system is that one of the fields in stat is the file size. So if you stat a file, the file system needs to figure out the size of that file and report it back to you. There's different ways to do this depending on your file system. One way is to have the file system keep a running tally of how big a given file is. That's inevitably going to be stored on one server. So if you have 40,000 processes that all call stat at once, it's going to go to one server, retrieve that little bit of information, and bring it back over the network. So you're going to have a bottleneck for that stat. The other option is that a file system can elect to not track the size at all until you ask for it, which makes a certain amount of sense. But that means that if you have 40,000 people call stat, it's going to contact all the servers to calculate on the fly what the size is. It's going to keep doing that over and over again. So, of course, file systems can do things to mitigate these. You can do some caching, maybe, play some games with semantics. But if you can simply limit the number of stats that your application does, file system doesn't have to work so hard. And the problem can be different on different systems, but at scale, stats just bad everywhere that I know of. So, I guess another thing to give you a flavor of what can be done with Darshan, what does it mean, not just from looking at an individual application, but what do we do with it at the facilities? Because it's turned on for applications automatically, we have a big kind of historical record of logs that have been produced on machines, and we can mine through it now and then to look for either people that we need to contact to help them with their application, or just kind of learn something about how we need to procure machines in the future or what we need to research. So this particular graph shows analysis of about 128,000 logs from Mira that we did a while back, and all we did was plotted how many ranks the application used and how much data it moved. And you can see a few interesting things in there. So we can find out which application did the most data. So in this particular case, we found one that did 300 terabytes of reads and writes. We can see the biggest ones by scale. The biggest you can run on Mira is 768,000 processes. You see these bands because on Blue Gene machines, jobs tend to be a power of 2 to fit into the partitions, most effectively. And then every once in a while you see some kind of streaking across here that don't fit the power of 2. And inevitably this is someone doing a scaling experiment. They're trying to ramp up the number of nodes and plot some trend in their behavior. So sometimes we can see those appear. So, this is sort of this is a lot of different dissimilar examples of what you can see in a Darshan log and what might go wrong. But just to kind of distill it down into a few things, whether you use Darshan or some other tool, it's a good thing to do now and then to check and see if your application is doing what you thought it was, and see if there's some problems you can address. And at any facility, you can find someone that can help you with these problems. And from what we learned from Darshan is that you have to be careful to build a tool like that it'll scale. In the case of Darshan, we try really carefully not to share things between processes until we have to, and we really put a lot of effort into using collectives properly. The same things that an application would do to make sure that it scales. We do the same thing in our debugging tools. And I guess if I wanted to distill some simple, here's how you get fast I/O. These are the things that we've learned from looking at Darshan logs, the things that can help you. So first of all, use collectives if you can. This is the way that you get these optimizations like two-phase I/O and collective buffering that will help you kind of automatically aggregate your I/O. So that's a good thing to do. Using high-level libraries like ParallelNetCDF or HDF5, those not only make it hopefully easier for your application by giving you an API that matches your data model, but they encapsulate some more optimizations that we've talked about. Aside from that, if you have the ability to do large I/O instead of small I/O, maybe just by moving your write call to a different position in a nested loop and capturing more data at once, that helps a lot. Don't do too much metadata unless you need to. If you need to check the size of a file, have one rank do it at the end of your job or at the end of I/O. Don't have everyone poking at the file if they don't have to. If you're going to write shared files, by all means, use MPIO or use a high-level library. If you use just open, read, and write to do a shared file, especially when you're writing, you're going to have a bad time because it doesn't provide any information to the storage system to optimize, so it's just going to brute force process your operations. From the from the visualization example, we learned don't leave gaps in your file when you're writing unless you have to. If there's an easy way to organize it so that you're writing dense data, that makes things go faster. And last but not least, use Darshan to see what's going on. So that's sort of the Darshan portion of the presentation. I'm going to change tracks entirely here and talk a little more about sort of future trends to kind of give you an idea of some things that are coming in I/O and what some applications are doing so you can keep these things in mind. The first thing is, first topic is sort of trends in data analysis. So if you're running a simulation, you might be producing a lot of data and you want to come back and mine it later and find what the interesting points are, do visualizations, that sort of thing. And there's some different strategies for how to do that. So I'm using Mira as an example. This portion here is sort of the part of the system that we've been focusing on so far. Your compute nodes, I/O nodes, and your storage system down here. This slide's old, so it says Tukey. We have a system called Cooley now. That's our analysis system. Those are a little bit more like conventional Linux nodes with more memory, GPUs, and that's where it's intended for analysis to be done there. So when you have a big application that's going to be using this model, it's going to be writing some data, doing some analysis, the most straightforward way to do things is to have these two things be totally decoupled. Your application writes its data into the storage system, and then sometime later you read it back on the analysis cluster, Cooley, and you do some analysis on it. And it's easy to understand, and it works everywhere. Another trend that's coming, though, is and some applications do this. It's a little bit harder to set up in terms of administratively how to make this work, but it can be done, is co-analysis. So instead of having the analysis happen at a different point in time later after your simulation is run, you can actually schedule jobs to run on Mira and on Cooley at the same time, and they share data directly over the InfiniBand. So you're kind of cutting out the middleman of storage for your analysis. There's some downsides to this. This is more complicated. You have to code your application to make this work, and there's some libraries like Glean that can help you do this, or data spaces that can help you do this. But you're going to share the data directly and have the analysis happen at the same time. You still may have to do I/O for other reasons, but it may save you some of the I/O costs and get you a little bit quicker turnaround. If you go even one step further, it is possible to also cut out the analysis cluster altogether and do in situ analysis. So what happens in situ analysis is you either have routines or separate processes on your compute nodes that do the analysis right there while your simulation is running, and you don't even bother sending it anywhere. So again, there's tools to help with that. You typically end up doing using different libraries that are meant to scale to the compute node scale. You're not going to be running things that are for conventional small scale clusters there. But some types of data reductions and analysis can be done on the fly. So these are kind of strategies for just not doing I/O if you can help it. And an example, Rob talked about the hack code later or earlier. Hack is a good example of one that has been kind of trying out a lot of these different technologies, and they've used some of these analysis techniques. So what they need to do is they're working on particles, like Rob was describing, but some of the analysis they want to do, they need to convert it into a grid to do a different type of analysis algorithm on. And they can actually do this model where all the analysis happens on the compute nodes for a class of their analysis. And to do this, they use a toolkit called DIY, which that's another thing developed at Argonne, and I can put you in touch with someone if you're interested in it. And DIY can, on the fly, on the compute nodes, do a subset of the analysis and produce data that you can then explore with peer review. So that's just sort of I can't tell you a whole lot about the specific technologies or techniques in here, but just to give you an idea of what's out there and what you could be doing. Maybe something to consider in the future. Another trend that's coming, and will be here before you know it within several months, is in-system storage. So what in-system storage means is pretty much what it says on the tin. You get a little bit of storage actually in your compute environment before you get all the way out to the enterprise storage arrays. And usually this would be done with NVRAM, something that can be packaged pretty densely and has good performance characteristics. And in this particular example, the storage has been put on the forwarding nodes. So at least saves you the hops of going over the external network to the servers, to the file system. And the way to think of this is as a cache. It stands in between you and the file system to give you a faster path to do I/O before it gets out there. So this is the most obvious way to use this is to handle the burstiness of HPC applications. So what we tend to see happen is an application will compute for a while. It gets to a point, it's going to dump a checkpoint or dump an analysis file, and it's going to rinse and repeat, keep doing that over and over. So there are very few applications that have a continuous stream of I/O that they're doing. They're going to have these big times where all of a sudden they have to do I/O. So what the burst buffer can do in this case is absorb that burst and then trickle it out to the storage system over time, so that you can get on with your computation while the I/O is still happening. And we did an analysis. This is maybe 4 years old now, but we looked at some big application examples and looked at how big their bursts were. This was by mining Darshan data, and we saw there were a lot that would write as many as 30 terabytes is the biggest one here, but several that would write 100 gigabytes at a time, and then there would be some period of computation and they would do the same thing. So we would see these recurring patterns. So these are the big bursts that a large application might be dropping to the file system. So at the time, a few years ago, we didn't have a burst buffer on any of our deployed systems, so we did some simulation to look at what they would do. So I'm not going to torture you with the workflow here, but we have a discrete event simulation that can model these big storage systems and play games with where to put the storage and what the parameters of the storage are. And we used to look at this burst buffer example. And the net result is kind of easily summarized by these two graphs. One is with the burst buffer and one's without. The top one is without. And we showed a mix of 3 applications running at the same time that have these bursts with different characteristics. And what happened is, this is as you go across the x-axis, this is the time that each application spent doing I/O for a little bit. And this is how much bandwidth it achieved. So in the system we were modeling, we're getting in the tens up to maybe 50 gigabytes per second. This was Intrepid. And if we put just a relatively small amount of burst memory on the I/O nodes to absorb some of those chunks, these peaks could get up as high as 10 times the bandwidth that they would normally get, and get the application back to doing its computation a lot faster. So this particular model was not changing the file system at all. We were just imposing this burst buffer in there. So it could get you a pretty big win and cut the computation time for your execution time for your applications down. So that's all well and good, a simulation. What's it going to do for us now? Well, fast forward a few years, and this year we're going to start seeing burst buffers arrive at our facilities. NERSC is going to have the first one in the DOE. The Corey system, phase 1 is coming, I think November is the latest thing I've heard, and phase 2 will be coming next year. And what they've done is the burst buffers aren't on the forwarding nodes. They just have a set of nodes in the system that have these burst buffers on them. Data can go there and then bounce back out through the I/O forwarding nodes to the file system. And it's way faster than the parallel file system that's on there. And Cray is developing software to go along with it called Data Warp. Data Warp's already available. And that will manage sort of how do you get the data to and from the burst buffers. And the rate they're projecting is that this will get you up to 1.5 terabytes per second writing data out of your compute nodes. And that's not the only one. That's going to be the first one, but this is going to be the reality in a few years, that all the sites are going to have systems with burst buffers. The Trinity system at Los Alamos, Summit at Oak Ridge, Sierra, Argonne, we're all going to have burst buffers. They're going to be in different places, so they're not all going to behave the same in terms of their performance characteristics. The Oak Ridge and Lawrence Livermore Coral machines are going to have some storage in the compute nodes instead of on separate dedicated nodes. So every single compute node will have some amount of storage available. We'll have the same thing on the Aurora system, maybe not the same amount, and then also separate burst buffers elsewhere in the system. So what will this mean for applications? There's different ways that it could be used. Since these aren't in production, there's a little bit still up in the air. But you can provision the burst buffers for a given job. So when you get your job, you get a certain amount of burst buffer space. You can put things in your job submission script to migrate data to the burst buffer. So if you're going to read something, you can have it waiting for you in the burst buffer when you get there. You can use it transparently, so you don't change your application. You do the same I/O you've always done, and by the magic of software, it goes to the burst buffer. And so of course, initially especially, they don't want applications to have to change, but you may have to put some parameters in your submission script to kind of control what's going on. And it's another toy. We get to do some new things that we couldn't do before. So you can imagine using this for out-of-core computation, for helping with in situ analysis, because it gives you some extra memory essentially that you can use to hold data. And you could also, depending on what type of device you have, if you look back at this earlier chart, some of these machines are going to have NVRAM that's probably quite a bit faster than, say, a solid-state disk. And in that case, you can treat it like memory. It might be byte addressable for you to be able to just extend the memory that you have available in your application. So this is, I don't have any particular tips other than just to be aware this is coming, and that's what there's going to be. I'm almost out of time, but just a couple of minutes. We have some, in addition to changing architectures, there's some different data models that may be available in the future. So everything we do now ultimately ends up in a file and directory, but it doesn't have to be that way. If you go read any papers about internet services from Google or Hadoop, you see different ways of doing things. So you could be using key value stores, you could be using objects, there's graph databases, there's all these wonderful things out there. These are easier to adopt in internet services and kind of the open source environment because there's not so much investment in we've got one big multi-million-dollar machine and we must pick the storage system for it. They can be a little more agile. So these things aren't routinely available on, say, Mira, for example, but we're working on it. So we're kind of eyeing this landscape and figuring out which of these makes sense from an investment point of view to make available. This is something where you guys can help. If you're looking at these other data models and saying, gee, I really wish I could do key value stores for my application, that would be a good thing to let me know, and we'll take that into account. But it's almost certain that more of this will become available in the future. It's just a matter of when and which ones get there first. So just a few things to kind of wrap up the morning session. Stuff's complicated. It's a little bit hard to get the most out of it sometimes, but we try to provide some tools, whether that's a library to help you do these optimizations automatically or some debugging tools. We hope, if anything, we've given you some things that maybe you can be aware of, just so if you see something happen, you can refer back to the presentation and get an idea of what it means. If you guys catch me later, I'd love to hear what technologies are most interesting to you. What would you like to have heard more about that we didn't cover? We can make it better. So please just give us some feedback if you can. And thank you very much for your patience. And that's it.